My name is Isailović, and I will give you a short presentation on interface shear fatigue performance of asphalt pavement structures. This is also one part of my PhD work at University of Braunschweig. As you probably know, in order to ensure a good and durable bonding between asphalt materials or asphalt pavement layers, the surface of underlying layer is usually cleaned and covered with a thin layer of bituminous top coat material or bituminous emulsion. This material can be wired in art in a mold. For example, we have unmodified emulsion, polymer modified with high content of bitumen or low content of bitumen. Therefore, long-term performance and durability of asphalt pavements are highly influenced by prevailing bonding condition. For example, poor or missing bonding between two asphalt layers will result in a serious change of this three-dimensional stress state in entire structure and may provoke significant increase in the stresses at the bottom of asphalt layer, and therefore consequently an essential reduction of the structural barrier capacity, and therefore a much shorter service life is expected. Interface properties are usually evaluated in laboratory using monotonic shear test. You can see this shear test in this figure, and we apply a constant shear displacement rate across the layer interface. As a result of this test, we obtain the shear strength as a peak of the shearing force, and this parameter will be used for, or usually used for, evaluation. But this shear stress is not cyclic, and therefore long-term shear performance remains unclear. This test result cannot be appropriately used for modeling or for mechanistic pavement design purposes, and therefore we needed a new approach. We needed a procedure which is able to evaluate the interface fatigue performance, and which is also partially able to simulate the field conditions more realistically. As a basis, we also used monotonic shear stress, but with sinusoidal stress application, which is vertically, and additionally we applied compressive normal load, which is intended to simulate the vertical traffic load. Our goal was to obtain reliable interface shear fatigue functions which can be used for both evaluating of fatigue properties of interface bonding and differentiated between design choices of interface bonding. For this project, we applied many asphalt mixtures. As you can see, we have here binder curves on base curves, we have surface curves on binder curves, also base curves on base curves. We used also different top coat materials, C60, which was polymer modified, or C40. 40 means 40% of bitumen inside. And also we applied U60K, which is non-polymer modified. Also, there are also some different amounts of emulsion from 200 to 300 gram per square meter. Additionally, we changed also some test parameters. As you can see, we had a wide range on compressive normal load from 0 to 0.5 megapascal, and from the temperature from -10 to 50. That means we wanted to test all the conditions that can be applied also in situ. Firstly, we had to get the samples. The samples were attained from using a German sector compactor. We drilled the cores from these slabs. But these samples we cannot just put in the machine. We have to adjust them, and this adjustment is made using these 4 shelves. And this procedure is really, or has to be really carefully done, because at the end, if we glue the sample, there should be 1 millimeter gap that allows this sharing of the layers. When we got sample like on this figure, we are able to put this sample in our machine to use I would say 24 screws. And if we have the sample in the machine, then we are able to apply this vertical shear load, which is displacement controlled. This displacement is generated using these two LVDTs from both sides of the sample. And additionally, as I said previously, we are able to apply this compressive normal load in order to simulate the load also in situ. The frequency of sinusoidal loading was set on 10 Hz. Here on the figure, you can see 3 tests at different temperatures with 0 megapascal of compressive normal load and development of shear stiffness over the number of loading cycles. As a consequence of fatigue effects, you can see 3 phases of the stiffness decay in the test. The first phase, the rush decrease of the stiffness, then you have quasi-stationary phase, and then you have propagation phase. But you can also see that the shear stiffness remains at a really low level. That means it doesn't approach the 0. This is most probably attributed to the residual friction with the layer interface, while any other effects from adhesion and interlocking are relatively low. Number of loading cycles or fatigue life is calculated at the number of loading cycles where shear stiffness reach 50% of the initial value. On next slide, you can see also test at 20 degrees, but with different stress levels. You can see the test without normal stress with 0.25 megapascal and with 0.5 megapascal normal stress. But you can see here no propagation phase is observed. That means that this horizontal stress we applied on our sample provokes confining and makes friction, adhesion, and interlocking effects more effective. You can see that the higher the horizontal stress is, you have increased stiff shear stiffness at failure. Since it is the first test we developed at TU Braunschweig, and we didn't have any experience with with this type of test. That means we should develop procedure. How can we apply our different displacement amplitudes? And this we did with amplitude sweep test. And amplitude sweep test, that means stepwise increase of our displacement amplitude until the failure of the sample within 25 steps and with 200 cycles in each step. You can see on the next figure one example of this amplitude sweep test. You can see that our displacement amplitude is increasing over the time, and the force needed to achieve this displacement amplitude is also increasing until one moment where drastically decrease is noticed. That means we have here a boundary, and using this displacement amplitude in fatigue evaluation wouldn't be so reliable because our sample would broken within a small number of loading cycles. Therefore, for our fatigue evaluation, we are able to use or to choose in this, from these first phases, and therefore 3 displacement amplitudes are taken into consideration for fatigue evaluation. So we have 3 amplitudes, displacement amplitudes, and we also have 3 test repetitions for each amplitude. That means we are able to develop fatigue line that is able to also to give reliable result on fatigue evaluation of shear performance. You can see the higher displacement amplitude is, the lower fatigue life is. If we add to this fatigue line another fatigue lines at different stress or different stress amplitude, we can get the dependence of fatigue performance on horizontal compressive normal load. And you can see that this is test conducted without any normal load. This is with 0.25 and this is with 0.5. That means with increased normal load we are moving to this right side. That means we have improved bonding effect in the shear interface. If we observe these different temperatures, we can also see that the test at 0 or at 10 degrees, they show the best fatigue properties. But fatigue tests at 20 and 30 show for different test pavements also different impacts. And fatigue tests at -10 and 50 didn't lead to the reliable test results because the tests are either too long or the results are not reliable. Therefore, we had to choose between optimum test parameters, and we have chosen the temperature of 20 degrees because this temperature leads to the lower result scattering, and we also applied normal stress of 0 megapascal. That means no axial deformation of the assembly are observed. What does it mean, this no axial deformation? You can see here that the normal load applied press the double layer samples in a horizontal way and induce this displacement amplitude in horizontal direction. That means that we have to control this horizontal deformation because in case of over displacement exceeding 1 millimeters, this steel blocks would run against each other. That means that would lead to the damage of the machine, and we don't want that in our tests. Now I will show you some results at optimal test parameters at a temperature of 20 degrees and normal stress of 0 megapascal. You can see here bonding with C60 polymer modified emulsion, and you can see that this line show the better fatigue properties than this line. That means if we apply C60 polymer modified emulsion, it would lead to the better bonding than if we applied a non-polymer modified emulsion with a lower content of bitumen inside. If we add the test, so these red lines, it was bonding surface binder. But if we add binder base, you can see that our binder base bonding is even lower than surface binder. That means that the ranking is in accordance with practical experience. Therefore, the following can be concluded. We developed a new procedure for evaluation of interface phase fatigue performance. We also obtained unique shear functions for the investigation of fatigue. Also, we saw that these parameters are highly dependent on the compressive normal stress application and also on temperature. And as a conclusion, it was found that optimal evaluation of interface shear fatigue is possible at temperature of 20 degrees and without application of normal stress. Thank you very much for your attention.